Dear children, in the previous class, we have studied about the various gas laws, that is the Boyle's law, Charles' law, Gay-Lussac's law and Avogadro's law, and how the pressure, temperature, volume and the number of the moles of the gases are related. The gases which obeys all these laws strictly are known as ideal gases. The three laws can be together in a single equation which is known as ideal gas equation. At constant temperature and the number of the moles of the gas, volume is inversely proportional to the pressure, it's Boyle's law. At constant pressure and the number of the moles of the gas, volume is directly proportional to temperature, that is Charles' law. At constant pressure and temperature, volume is directly proportional to N, that is Avogadro's law. When we put together all these three laws, the equation will be PV equals to nRT, where R is the universal gas constant. It is same for all gases, therefore it is also called universal gas constant. At constant temperature and pressure, n moles of any gas will have the same volume because volume is equals to nRT upon P and nRT and P are constant. This equation will be applicable to any gas under those conditions when behavior of the gas approaches ideal behavior. All those gases which obeys the ideal gas equation are known as the ideal gases. But actually the gases don't do so, and then they are known as the real gases. Ideal gas equation is a relationship between the four variables and it describes the state of any gas, therefore it is also called equation of state. If temperature, volume and pressure of a fixed amount of gas vary from T1, V1 and P1 to T2, V2 and P2, then we can write P1, V1 upon T1 is equals to P2, V2 upon T2, is used to find out any of the 6 variables if 5 variables are given. The next is the Dalton's law of partial pressure. The Dalton's law states that the total pressure exerted by the mixture of a non-reactive gases is equal to the sum of the partial pressure of the individual gas. For example, if we mix 2 or 3 or 4 gases which are non-reacting, then the total pressure will be equals to the sum of the partial pressure of each of the gas. In the mixture of the gases, the pressure exerted by the individual gas is called the partial pressure. P total is equals to P1 plus P2 plus P3 and so on at constant temperature and volume. Now, the aqueous tension. Aqueous tension is the pressure exerted by the moisture. When we collect the gas over the water, the gas becomes moist. Then the total pressure also includes the aqueous tension. If we want to find out the pressure of the dry gas, then pressure of the dry gas is equals to P total minus aqueous tension. Dear children, after all the gas laws and the ideal gas equation, let me tell you about the kinetic molecular theory of gases. As per this theory, the interactive forces between the gaseous molecules is almost negligible. Also, the volume of each particle of the gas is also negligible or nil as compared to the empty space between the various gaseous molecules. And these two main postulates are responsible for the deviation from the ideal behavior. As per this kinetic theory of gases, also the molecules of the gases are in continuous motion. They are continuously moving and they are colliding with each other and with the walls of the container, and that is responsible for the pressure exerted by the gas. The kinetic molecular theory says that the collisions are perfectly elastic. Perfectly elastic means there is no loss of energy or even no gain of energy also. Let's see the postulates one by one. The postulates of the kinetic molecular theory of gases provides a microscopic model gases. Gases consist of large number of identical particles that are so small and so far apart on the average that the actual volume of the molecules is negligible in comparison to the empty space between them. And this so much of empty space between the gaseous molecules is responsible of high compressibility of the gas. The second postulate: there is no force of attraction between the particles of a gas at ordinary temperature and pressure. That is why when there is no force of attraction, the gaseous molecules are freely moving. They fill the whole container in which they are put. Also, you can see any gas mixes with the other gas. Particles of a gas are always in the constant and random motion. Particles of the gas move in all possible direction in straight lines. During their random motion, they collide with each other and with the walls of the container. The collision of the gas molecules are perfectly elastic. This means that the total energy of the molecules before and after the collision remains same. The perfectly elastic collisions is also responsible for the stability of the gaseous state. Next postulate: at any particular time, different particles in the gas have different speeds and hence different kinetic energies. This assumption is responsible because as the particles collide, we expect their speeds to change. If a molecule has variable speed, then it must have a variable kinetic energy. In kinetic theory, it is assumed that average kinetic energy of the gas molecules is directly proportional to the absolute temperature. As we increase the temperature, the kinetic energy of the molecules, that is the gaseous molecules, increases. Behavior of the real gases. The gases which we come across are the real gases. It means they are not strictly following the Boyle's law, Charles' law and Avogadro's law. Deviation from the ideal gas behavior. Deviation from the ideal behavior also becomes apparent when pressure versus volume plot of the experimental data, that is real gas, and the theoretically calculated from the Boyle's law, that is ideal gas, should coincide. When we plot a graph for a real gas and for the ideal gas, they must coincide, but actually it does not happen. Real gases show deviations from the ideal gas law because molecules interact with each other. At high pressure, molecules of the gases are very close to each other. Molecular interactions start operating. Kinetic theory of gases says that intermolecular forces between the gases is negligible, but actually this is not the case. When the pressure is high, there is a considerable amount of intermolecular interactions, and that is why we don't have ideal gases. Repulsive force also becomes significant. Repulsive interactions are short-range interactions and are significant when molecules are almost in contact. Real gases show ideal behavior when conditions of temperature forces. Also, as per the kinetic molecular theory of gases, the volume of the gas molecules is negligible as compared to the empty spaces. It is also not actually the case. The gaseous molecules have volume. We cannot ignore the volume of each molecule. So, these two points of or the postulates of the kinetic molecular theory of gases, that the intermolecular forces are negligible and their volume is also negligible, is the reason behind that why the real gases are not behaving as the ideal gases. We cannot ignore their volume, and there is considerable amount of the forces of attractions or repulsions between these gaseous molecules. The real gases can behave ideally when the pressure is very low or when it approaches 0. Now, the next topic is the compressibility factor. The deviation from the ideal behavior can be measured in the terms of the compressibility factor Z, which is the ratio of the product PV and nRT. Mathematically, Z is equals to PV upon nRT. For ideal gas, Z is equals to 1 at all temperatures and pressures, because PV is equals to nRT for an ideal gas. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to it. So, when a real gas can behave as an ideal gas, now we have the 2 points. Either the volume should be very high or the pressure should be very low. Now, the boil point. The temperature at which a real gas obeys ideal gas law over an appreciable range of pressure is called boil temperature or boil point. Boil point of a gas depends upon its nature. Above the boil point, real gases show positive deviations from ideality and Z values are greater than 1. The forces of attraction between the molecules are very feeble. At low pressure and high temperature, gases show ideal behavior. These conditions for different gases are different. We have studied the ideal gas equation, in which we combined the gas laws. We combine the Boyle's law, Charles' law and Avogadro's law. As per the ideal gas equation, PV is equals to nRT. P is pressure, V is volume, N is the number of the moles of the gas, R is universal gas constant and T is temperature. But actually the gases are real and they do not behave ideally, because ideal gas is the gas which obeys all the laws strictly. We also studied about the kinetic molecular theory of gases. As per this kinetic molecular theory, the molecular interactive forces in between the gaseous molecules is negligible. Also, the volume of a gaseous molecule is nil. That does not hold true. A real gas can behave ideally when the volume is very high and temperature is very low. I am sure, dear children, that all the things and all the concepts are clear to you.